And the final thing of this lecture, which was probably the hardest, but hopefully these first two things have introduced you a little bit to the idea, is that I want to introduce the idea rigorously of a limit of a sequence of functions. Now, you could think that everything you've learned so far, starts off that you define a calculus limit. It's analogous to what we did at the beginning of the class. Then, okay, you refine that in 131a, you talk about limits of sequences, real valued sequences. So xn is just some numbers in R. And then in our class, we have already generalized to metric spaces. So xn can be an element of Rd or a general metric space x, just as long as we have some notion of distance in the space. But the real goal, what we're doing now with most applications, is we want to talk about limits of a sequence of functions. Well, technically, there is much more you could do, much more weird statements you could do. Perhaps the most confusing is you can talk about, and I've mentioned this in some supplemental videos at least, limit of a sequence of sequences. But mostly I don't want to talk about that. I want to talk about sequence of functions. So the first thing to understand with that is that the object that is converging is functions, f and x. We are looking at in what sense does this object converge. And the space of functions is very infinite dimensional. And whenever you have an infinite dimensional space, then there are many notions, competing notions of convergence, and you have to be clear and careful about how things converge, because sometimes they converge in one way, other times in other ways. So depending on your application, you'll have to use a different notion. So we'll begin to understand two ways in which a sequence of functions can converge with different properties, and these are called pointwise and uniform convergence. Any questions, by the way, feel free to interrupt or ask in the chat. Okay, so let's define these. So we're working, our space of objects is a space of functions. So we're looking at, we have fixed some k. K could be any metric space, and we are looking mostly at real valued functions. Again, if you want, you can put a y there. Everything generalizes directly, but mostly applications concern real valued functions, and that's hard enough. So I recommend restricting to that. And you can talk about convergence of any type of functions, but again, for simplicity, it's complicated enough to mostly talk about continuous functions. Some of the statements I will say will hold for not continuous functions, but mostly we're interested in continuous functions. And a lot of the time, the domain of these functions will be compact. There are many reasons for this. Many of these come back to this theorem, actually. That if you don't have a compact space, then you can't hope for uniform convergence in practical applications. So usually it's a compact space, but there's no need to it again. So some variability here. You can vary the domain, you can vary the target. In general, you could have functions between two metric spaces. And what do we mean by convergence of a function to another function? The simplest way to define this is to define the so-called pointwise convergence. And well, you could argue whether it's the simplest way, but what it means is that you fix a point, and then you get a sequence of points, f and x. And this is a sequence of points either in a metric space, or in our case, these are real numbers. So we can ask, when does this sequence of values converge to some limiting values? So we say that fn pointwise converges to f if the following holds. And this is sometimes, I'll denote this by Fn single arrow f, and often emphasized by saying pointwise. So this means that you fix a real value x, or an object in your metric space, and you insist that the sequence of real values converges to that real value. Okay, this is a notion. There's no reason that this could be interesting, but let's see it in action, what it looks like in some cases. So I've divided here, you have a sequence of functions, 3 examples. Find the pointwise limit, let's draw a picture of it, and let's observe some interesting phenomena that happens along it. So, okay, and remember, if you're fixing an x, so fix an x, if we take limit as n goes to infinity of square root x squared plus 1 over n, well, what we get is that square root is a continuous function, so this is the same thing as square root of x squared, which is absolute value of f of x. So we would say that Fn of x converges to absolute value of x pointwise. And we could call this function f of x, the limit function. Okay, well, what does it look like? These are square roots of x squared plus 1 over n. They are just a little bit above the x-axis when n is very big. And they limit to this absolute value function. So this is f. And let's draw the other ones in a different color. So we have our fn's in purple. What will they look like? Well, they will be close to the function because they are converging, but they're a little bit smoother. They're kind of smooth out versions of f. Something like this, that are decreasing to f. Why they are decreasing? Because for every x, this forms a decreasing sequence of functions. Okay, now what is the behavior that I want you to extract from this example? Is that fn are differentiable, but f is not. Now, okay, let's look at it. Let's skip one of these, or do it very quickly. So in this case, well, what is happening, as n goes to infinity, the denominator goes off to infinity, so these functions converge to 0. Well, what do these graphs look like? Each of these graphs looks like asymptotically something like x cubed, so you have some graph that looks vaguely like something like that. It doesn't really matter exactly what it looks like, but as n goes off to infinity, these get pushed towards the x-axis. So this indicates that the speed of convergence can be different in different parts. So, okay, everything here will tilt towards the 0 function, but at different speeds. So if you're far away, you don't converge very quickly. And finally, one more example is if you, even in bounded domains, you can have this kind of behavior. So if you take 1 minus x to the n, and we take the limit of as n goes to infinity, well, this is the limit of 1 minus x to the n. Now this is a power of something between 0 and 1. Then there are 2 choices. If x is equal to 0, this is 1 to the n, and it's a constant sequence 1. It converges to 1. But if x is in the interval, half open interval 0 to 1, then this base of the exponent is strictly less than 1, and therefore the higher powers will converge to 0. So f of n converges pointwise to f, which is defined as 1 when x is equal to 0, and 0 when x is equal to 0, 1. So what does this look like? So if we draw the graph, well, we are only interested in values between 0 and 1. So these functions, they're always 1 at 0, but what really they're doing? They're converging mostly to 0, except at that point 1. And in the limit, you converge to this blue graph. So you get this sequence of things that goes down, except that they grow very rapidly close to 0. And what this behavior is showing is that Fn are all continuous, but F is not continuous. So you see, yeah, go ahead.
So does this tell us that like the set of continuous functions isn't closed?
It's not closed under pointwise convergence.
Okay.
So you're right. If we're sloppy about the notion of the convergence, it becomes not closed. Exactly. Yeah. You have a sequence of things that converges to something that's outside the space. Exactly.
Okay.
If we define pointwise convergence. So continuity can fail. This is also showing differentiable functions that are not closed because you have a sequence of things converging to something that's outside the set. Well, this one is not really showing us such a behavior, but this is a slightly different phenomenon. But good, excellent question. Excellent question. Yes, it's very disconcerting. We would like to have a closed set, a closed metric space. I mean, here you have a sequence of things that converges outside the metric space, especially if we're only interested in continuous functions. So how do we repair this? And this is what I will give you an answer now, and we'll do more of it on Wednesday, is that we have to define a different notion of convergence which preserves these properties, which preserves continuity, differentiability, integrability. Pointwise convergence does not converge. So pointwise does not. And it doesn't give you a closed space. Exactly. This is kind of a good way of expressing that issue. And another issue that you could say is that if you want to exchange limits, or if you want to exchange integrals and limits, when is this hold? And the answer is always, you have to have some uniform estimate that this convergence has to occur at the same speed everywhere. It cannot be like this, that some values are converging very slowly, whereas others are converging faster. Everything should be approaching roughly at the same speed. So usually the answer is uniformity. And how do we define that? It's a little bit different than pointwise, but just by the order of quantifiers, just like in the uniform continuity. So we say that a sequence of functions converge uniformly to F if for every epsilon positive, there exists some capital N, so that if N is bigger than capital N, then no matter the point you choose in K, distance, or these are real valued functions, so this is just Fn of x minus f of x is less than or equal to epsilon. Yeah, of course, you could write the distance if you wanted to generalize this to higher things. There's really no need to. So this is a more robust notion. It behaves much better. It precludes some of these examples. So again, let's contrast this with pointwise continuity, that there, for every x in K, for every epsilon in positive, there exists an N such that if N is bigger than N, then for this particular x, the function values are close. But here, you require that the same N works for all x. Whereas here, the N can depend on x. So an example is, for example, this sequence. This converges pointwise, but not uniformly. But this excellent question that was asked about continuity is, I can answer it by a theorem, except I didn't state the theorem. So let's state it now. and that will be the last thing of today. If you have Fn from K to R, or to any metric space, are continuous, and Fn converges uniformly to F, K to R, then F is also continuous. So uniform convergence does preserve continuity. And that's why if you want to define a metric space, if you want to study the space of continuous functions with the notions of this class, then you should use uniform convergence. And there's a metric related to that we will talk more about on Wednesday, perhaps a little bit on Friday, in the videos for Friday. So it's an excellent, yeah, with that, we get closedness. So the space X that we defined becomes closed in a sense. I mean, in the space of all functions. Strictly speaking, if you have X as your space, then it's a full space is always closed. But now there's a useful exercise, but we don't have now time for it, is that if you have this sequence 1 over x, 1 minus x to the n, this does not converge uniformly. Well, the limit function is not continuous, so by this theorem, that has to be the case. But it's also a useful exercise to see how that works on its own, but I won't do it now due to the lack of time. Maybe the TA might do it later. So if you have any questions, feel free to stick around. But this was the end of the lecture.